Hello everyone, my name is Naveen Dar. I'm a high school student from San Diego, California, passionate about bioacoustics, and I'm very excited to present to you all today at Living Data 2025, my project, towards real-time rainforest gunshot detection. I'll start with a brief exposition of the problem, share my methods and results, and lastly conclude with plans for future work. So wildlife poaching is still a severe issue with many cascading consequences. It can lead to species decline and extinction, which causes ecosystem-wide destabilization as keystone species are pressured due to poaching, augmented by the fact that poaching is often a gateway to illegal deforestation, which can cause habitat loss. This can cause a great loss of ecotourism revenue, with an estimated $25 million per year lost due to poaching in Africa alone. But perhaps most importantly is an incalculable loss that you can't put a fiscal value on, a loss of intrinsic value and cultural heritage attached to the ecosystems and species pressured due to poaching. These issues, among others, makes poaching one of the greater contributors to biodiversity loss. And in some statistics, such as African rhino poaching rates from 2020 to 2023, poaching is in fact on the rise. But so is the potential for acoustic monitoring to make waves in how we map, understand, and track the spatial temporal trends of poaching and other anthropogenic activity in the rainforest by listening to the sound, such as gunshots, trucks, or even chainsaws. However, this can only help us paint a better picture of where poaching happens retrospectively. What if there is a way to detect poachers autonomously, in real time and for a low cost, helping the rangers intercept poachers immediately instead of playing a game of cat and mouse? Passive acoustic monitoring may hold the answer, but we have to modify the existing systems of it. They use audio capture with arrays of microphones deployed in rainforests, which are later then processed by a large, high compute cost neural network. However, these neural networks, because of intrinsic challenges with the task of rainforest gunshot detection, often has high false positive rates. Because of these issues, these existing systems have made it retrospective. If we want an eventual real-time system, we could use a low-footprint deep learning model that runs onboard 24/7 a microprocessor that is connected to the microphone. And we could leverage the predictions from multiple sensors in the same array through sensor integration in order to get a weighted and more accurate final prediction for gunshot presence. These two bottlenecks comprise the main components of my research. To train a lightweight model from the ground up to address the high computational costs of existing models, and to investigate sensor confidence integration as a way to reduce the high false positive rates for this task. The datasets I will be using are a train and validation dataset collected by the University of Southampton in the United Kingdom in Belize, and a smaller test dataset from Vietnam collected by the District of Forestry in Vietnam and the Kay Lee Siang Center for Conservation Bioacoustics. Investigating this dataset through spectrogram visualization revealed large intra-class variance in signal-to-noise ratio, frequency ranges, and saliency. However, even in this variety of gunshot signals, there are a few factors and features that remain constant across all gunshots, and I use those to help me inform what the model should learn and how. So the spatial features of a gunshot can be captured through 2D convolutions and pooling layers. The sharp spike or onset of a gunshot can be captured through 1D convolutions, and the sequential aspect of a gunshot signal, the fact that the initial blast is always followed by a decay in energy, can be captured by a recurrent neural network layer. Also, choosing the right input can make a big impact on model performance. I chose to use log MEL spectrograms as my input, as not only did it reduce the frequency dimension, which will make the model more lightweight, but it additionally, through the log scaling, made the features that I want the model to learn more salient compared to regular MEL spectrograms or linear spectrograms. Domain shift is a large and very real problem in this task of rainforest gunshot detection. To help the model generalize, I utilized extensive waveform and spectrogram-based augmentations during the training process. The final architecture I chose comprised of a stack of 2D depthwise-separable convolutions, which are a more lightweight form of 2D convolutional layers, followed by max pooling, and then a reshaping so that it can be inputted into the stack of 1D convolutions and then the gated recurrent unit, which is a lightweight version of the recurrent neural network. Before training the custom lightweight network, I first obtained a baseline by training a purely 2D convolutional neural network, and then I evaluated and compared the two. So let's start with sensor integration. What's the motivation behind integrating the predictions from multiple sensors in an array? It stems from the fact that gunshots are very similar acoustically to other commonplace sounds in the rainforest, such as branches snapping, water droplets hitting the microphone, or even low-frequency vocalizations of frogs. However, gunshots are unique in the sheer amount of energy they have. As illustrated by these figures, a lower energy acoustic event that can cause a false positive will not propagate to sensor B and sensor C, which are a further distance away, meaning they won't be fooled and only sensor A will. Whereas a gunshot signal, because of the higher energy, will propagate further through the rainforest and be picked up by sensor B and C greater than the lower energy false positive event. Thus, my hypothesis was that a sensor analysis and integration layer, which is what I call the sensor integration function, or SAIL, can help reduce these lower energy false alarms. The criteria I made for this function was that it has to boost sensor agreement across the sensor array, penalize confidence but isolated predictions, produce a continuous output from 0 to 1, and scale to any amount of sensors. The graph and equation you see here on the right describe the function I end up finalizing with. It considers all unique pair of sensors and multiplies and then sums those multiplications of the probabilities that there is no gunshot, which is then normalized by the total support for gunshot presence, creating a measure of how likely it is there is no gunshot. This is then inversed in order to get a measure of how likely there is a gunshot before being applied to a sigmoid function in order to smoothly map the outputs from 0 to 1. To illustrate how this SAIL function works with a few examples, in this case with the low energy false positive, sensor A might be fooled and produce a 0.9 prediction, but sensor B and sensor C have lower predictions at 0.2 and 0.1 because the signal did not propagate there. Because of this isolated and confident prediction, SAIL penalizes it, and therefore the final decision is no gunshot. Whereas in the case of a gunshot, if sensor A and sensor B pick it up because of the higher energy, with predictions of 0.9 and 0.7, even if sensor C did not pick up the gunshot signal, because the majority of sensors agreed, then the SAIL function boosts that agreement and produces a 0.8 final prediction, or gunshot presence. To evaluate the SAIL function, I utilized randomized augmentations on multiple copies of each waveform from the Vietnam test dataset to emulate an array of 3 sensors per original waveform in the dataset. So I made 3 copies of each waveform from the Vietnam test dataset, created gain transform and Gaussian noise and time shifting augmentations, and then ran the trained model to obtain probabilities for each one before inputting those probabilities to the SAIL function. And doing that across all waveforms in the dataset comprised of 1 run, and I ran 1,000 simulation runs across this dataset. I also performed statistical evaluation in order to find if there was a significant difference between simple inference and the SAIL method. So I found a per file false positive rate by aggregating the false positive rate per negative file across all 1,000 runs, and then measured the difference between the mean false positive rates per file with inference and SAIL before running a Wilcoxon signed rank test on that distribution. But before we get into the results of the SAIL simulation, let's first look at how the network did. The baseline 2D convolutional model performed pretty well with a 0.819 f1 at 12 megabytes. However, if we look at these precision recall curves, which ideally we want to be going all up and to the right, we see that it did not too badly on the Belizean validation dataset, although it had low precision at higher recall levels. But it did not generalize well to the spatially distinct Vietnamese dataset, as we can see the precision recall curve was not as up and to the right. Looking at the lightweight neural network that we trained, it achieved a much better precision recall curve on the Belizean validation dataset, obtained a 0.908 f1 at 11 megabytes, and a higher precision at that higher 95% recall. Additionally, we can see through the precision recall curve for the Vietnamese dataset, it was able to generalize to the spatially distinct dataset. Comparing this model with the leading work on the same dataset, or Katzis et al.'s pre-trained Resonant 18, we can see that we achieved a similar validation f1 at a fraction of the model size, 11 megabytes in regular form, and just under a megabyte in quantized form, enabling the practicality of edge deployment for real-time detection. Moving on to the results of the SAIL simulation, we can see here, displayed through scatter plots, which has the file path of the individual waveform on the x-axis and the confidence score of that corresponding waveform on the y-axis, the difference between inference predictions and the median SAIL predictions across the 1,000 simulation runs. a statistically significant difference was found between the false positive rates, as shown in the scatter plot as well, where we can see that the blue dots above the threshold, or the false positives, were crushed to zero through the sale predictions. Additionally, we can see that the already high confidence positive predictions through inference were boosted to have even higher final predictions through sale. In the future, I'll be collaborating with the Elephant Listening Project and training a model for gunshot detection in the African rainforests, and eventually helping with implementation of real-time threat detection. Thank you to the researchers who made their datasets publicly available, and thank you to Irina Tolkova from Cornell's Kaylee C. Yang Center for Conservation Bioacoustics for guidance on this project. If you have any inquiries, please reach out to naveendar8030@gmail.com. Thank you.